joy. So today we're going to work on on the exercise that I didn't get the chance to do on Thursday, as well as today's exercise, which will go over things on this. How would lab be on Zoom? A lot like this. But usually the TA, we would just simply rotate through, with the TA would be rotating through the breakout room. But again, no idea. It is ostensibly, occurring on Saturday evening, which and is through Sunday. So depending on the timing, things would probably be clear. There'd be a lot of work on clearing things in preparation for Sunday. Sorry, for Monday. So lab 2 overview. Let's go. Sorry, not lab 2, but let's go ahead and do short exercise and this. So first things first, we're gonna have a bit of fun here with this over here. This is a link to your textbook. So I've just dropped it into chat. Otherwise, if you somehow missed that, go or are rewatching it, then just go to the your runestone.academy link, log in, go to the course, scroll all the way down, and we're going to do project 2 very quickly here. So one of the tools that we will be using in our class is something called the Turtle Graphics package. Okay. Once again, we're going to be playing with some black magic here. Don't necessarily know what it is, but we will be learning it. So this is not necessarily something you need to know now. It is something that you will be doing in lab 3, which means you don't have to really worry about it until later next week. I'll probably start talking about it on next Tuesday, and labs will start on that on the 30th. So not really something you have to worry about today. So the turtle is this very nice paradigm from the Logos programming language. It was meant as a fun way to teach children. Ooh, this is a nice graphic there. Fun way to teach children kind of programming by giving them a direct way to manipulate something. Basically, give instructions to a thing and make that thing move, right? And so and all it is that you give a little turtle, this thing over here, instructions. You give them instructions and ask them to, and the turtle follows those directions and moves. The directions are very simple. And basically the idea here is it will give us a way to visualize stuff. But what's cool is that we can run these Python programs in the browser. Yes, Alex, what's up?
Where could I find project 2?
Copy link, dropping it in chat again. There you go. Got it? So what you want to see is just simply see the chat. So do you see where the chat is? You can see it on the options on the bottom of the screen. And it should be audio, video, participants, and then chat. And there should be a notification there. Or it's going to be along to the side. Otherwise, you can go directly to Runestone. Okay. So what we're going to do now is we are going to see how this program runs. So operating with the turtle's fairly easy. What we do is we have this first thing called import turtle, which just simply says, hey, we're going to load up the turtle library, all the instructions for turtle. Why is this important? We don't always load up all of the Python packages. There's lots of them. And loading them up would make your program bloated and take up a lot of memory and possibly create variables that you didn't mean to create. So instead, we import things as we need it. Okay. Those things are things like, let's see. Those things are things like server. They're things like science packages or graphing packages or the image package, and in this case, turtle. So there's only really going to be two lines of Blackmagic. The first is this import turtle, which we'll learn more about next week with imports. And then we've got line 3. My turtle is equal to turtle.turtle, and the capitalization here does matter. Lowercase, and as you'll eventually learn in 1068, this is the constructor for a class. This makes a new turtle object, which is just to simply say it's making our turtle. We've got this thing called my turtle. Now, I prefer to give my turtle a bit easier of a name, a bit easy of a variable name, so because it's 3 letters to type in one syllable. And also, it doesn't look like I'm saying turtle, turtle, turtle a bunch of times in a row. So there we go. All right. Everything else is commands that we'll learn and make sense with. So what we're going to do here is we're going to see, okay, this one, line 5, bob.color green sets the color. There's a lot of things we can do here, but the most trivial thing is just giving it an actual color name and seeing that, oh, if we change it, the color name, we can change it. This one's a bit hard to see because, of course, there. Now, if I don't have this line of code here, the default color is just black. Make sense? All right. Next, let's go ahead and actually comment out and just kind of comment out everything so we can see. The most simple command for a turtle is telling the turtle to move forward. Like that. And we can see him animate forward. Let's go ahead and tell and give this argument a bit of further depth. We can see that he moves forward a bit more. So bob.forward, and then you provide an amount in that function. That amount is not millimeters, not inches, not any kind of normal distance, because every computer screen is different, but the one thing we can rely on is that they're all drawn with pixels. So that tells him to move 10 pixels forward. Bob.up lifts the tail. So let's explain what we're actually looking at over here with the help of another command I like to do. Bob.shape turtle. Because this is a turtle program. Might as well make him look like a turtle. That's what shape does. It changes the shape. Bob.forward. Draw a green line. Up. Lifts the tail. So what we're doing is that we are looking with a bird's eye view down at this turtle from the top. And this little turtle has a pen or a paintbrush attached to his tail. And as he moves, he drags this paintbrush along behind him. That's simple. Now, sometimes we want him to move without drawing. So in which case, we tell him bob.pen up, or we can just simply say up for short. Bob.up, which tells him to lift his pen up. So he moves forward 50 pixels. Then we tell him to lift his tail up, and then we tell him to move forward another 50. Pen up also works, by the way. And as you might imagine, I'm just going to copy and paste this for a second. Down. I don't need to save anything. Hold on. There we go. One second. I'm reflexively hit save. So let's see what's going on here. Stop share for a sec. What did I do? Control 5. There we go. Let's go ahead and just share this portion of the screen. That should be easier for everybody to see. Right? And so now we can see up. Sorry, we move forward, then we tell them to lift the tail up, then we tell them to put the tail down. The other commands are move right or turn right, as well as turn left. And that gives us a number of degrees. And just like there's a forward, there's a backwards too. Let's speed it. Let's slow this down so we can see it in a bit easier animation. So here we told him to move forward 50, move his pen up, move for another forward 50, move his pen up. So 50, another 50. And then he turned. And then he moved backwards. Okay, so we have all sorts of different controls with this. And in case you have just been trying to follow along wildly and it all got messed up, remember, you can always rewind to the beginning, the original program. I can also do things like this. Hit share code, which will send it to all 103 of you, apparently. And then if you reload the page, it will be there in your timeline at this time. So if you saved after I shared it, then you just have to back up a bit. That's fine. So your task for the next 10 minutes or so is to have fun, play around with this, draw something, be a square or a triangle or a smiley face. Next 5-10 minutes. Got it? And then we'll move on to the next program. Okay, this is meant to be a fairly straightforward exercise. Don't, again, follow the advice here. And the instructions are forward, backwards, left, right, up, down, essentially. Color. And if you want to look up more, you just go to turtle docs Python, and I'll drop this link in the chat. And this is the formal documentation, which is still a bit above our level, but hey, this has everything you would ever want to know and more about turtles. So I'm going to go ahead and pause this recording while you all go ahead and work on that, and I will be right back. Stop. I need to stop sharing. Okay, so to whoever just sent me that image, that is a problem I've not seen before with access denied to Runestone. Yeah, try logging out and then logging back in. Otherwise, yeah, so follow the directions on the page, which say try hitting the log out button. Okay, let's go ahead and share for a minute. Okay, right. So share screen. Right. So I've not seen this page before, but let's follow the instructions, right? You want to hit the log out button to log out and then try and log back in because web browsers can be weird sometimes. And then as it says, if the problem persists, try clearing the browser history, which is a bit more advanced, but you can clear out your history, which is a useful thing. As you never know when somebody sends you a link and you click it and it sends you to the crazy part of the internet. And you're like, no, FBI, I don't live there. So oh gosh, that reminds me. There was once a website called Mess Up My Search History. And what it would do is that it would basically just back to back load your Google search results with stuff that you would definitely not want on it. That would basically say, "Hey, you're getting on a watch list now." It was uh the internet was different back then, but also not. All right, so hopefully you've had the chance to um take a look at all these problems. Not take a look at the problems. To draw something, right? So let's go ahead and take a look at this problem. So this is probably our first actual like computing program that we're going to be doing, where we're going to actually be doing work involving the stuff we learned. Okay. We're going to also be learning about a specific type of problem that is rather annoying when it's asked, but because we don't talk about it in school, it's not the kind of stuff you get trained to do. But fortunately for you, I'm here to elucidate that matter. So first, input, compute, output. This is basically the kind of flow of the way the programs work, which is that you ask and this is a lot of programs where you ask the user to provide some input. You do a bunch of computation on it, and then you provide them with some output. This can be in computing, right? A lot of that time is that's doing math or basically telling the computer to do math for you because math is hard and I don't want to do it. Um, but it can also be like, getting only certain fields from a table, which can be very useful. So what we're going to need to do is that we're going to first take a problem that's going to look very familiar, and then we're going to look about another problem, which is all about making and documenting simplifying assumptions to complex problems, and how to make solve a problem from generalizing from a simpler version. All right, so here we've got a common computational problem, and it is this program over here that is suspiciously familiar to one of the programs we're going to need to deal with. Enter a number of years, and I'll tell you how many minutes that is. I'm going to go ahead and reduce this. Enter num years. I'll tell you how many minutes that is. I just wanted to make sure that we got onto one line. And what this does is that this entire program I'll have to try to help you out afterwards there. I wouldn't worry about it. Just follow along as best you can. All right. So what we're going to need to do is we've got years is equal to enter number of years, and the entire point of this program is to compute how many minutes. So we're going to run it just to kind of show you. Let's go ahead and give it 3 years, and it will tell me 3 years is 1.5 million minutes about, which is somehow less than I thought it would be. Go ahead and delete this extra space here. That always bugs me. Okay. And so how does this program do it? Go from years to minutes, right? Well, first things first, it asks the user for an input. Then it does magic, the computation. Then it does the output. So I'll break it up into those three parts. Input, compute, output. Input is pretty much always that input statement. Now, later on, we'll figure out better places to put the input statement. And then we do some computation. Later on, we'll learn, okay, when we do stuff, that's going to basically go into a function. But for right now, we've got years, and we've got this we've got this computation, and then we print our answer. So first thing we need to do is look at these first two lines here, where we ask for an input and we do this years equals int years. And to show why we need this line, we can just easily remove it and see why we need it. 3. 3 years is what? What? I knew what that happens. I'm just comedic effect, obviously. It's still going. Still going. Let's instead switch this up a bit so that we actually get an error this time rather than doing that. 3 years. Oh, it does work that way now. Fun. Wait a second. Yeah, it does work that way now. 3 years is this. So we are getting 365 plus 84 threes thrown in there. Why? Because when we take an input, years is a string, right? Anything we get from input is going to be a string. So what we want to do is we want to convert that into a string. Sorry, from a string to an integer. Now, I've got a question. What does the hash mark do? This is the comment. You'll see me using a whole lot. It turns basically anything after this symbol gets ignored by the computer. You'll see me do that a lot to kind of turn off the code for that line, as opposed to just deleting it. So without this code line here, we don't get what we expect. With this here, the computer's actually able to do the math. So you can see here, years is equal to int years, days, years. Couldn't I do it like, and another great question, couldn't I just do it like this, right? Right? Was that what you were asking, Gideon? Right. And then we wouldn't need this. Now, the reason that we do this, at least right now, is because this is scary early on. It's a lot going on. It's nested parentheses. So that can be very scary early on. So at the beginning, I like to, for pedagogical reasons, I like to split it up line by line. Nothing wrong with doing it either way. Okay. So now that we've figured out, okay, we've got our input. Yes, Alex.
Where could I find this chapter?
Here it is in chat again. Whoops. I accidentally bolded it, but that shouldn't matter. Just makes it seem
I kind of lost it on my end for some reason.
It happens. Don't worry about it. Don't worry about it. Using float would accomplish the same thing, right? Yeah, pretty much. Yeah, there's the only difference is that we're going to have a decimal point in there too. See, that's the only difference. Nothing wrong with using float instead of int in this particular case, right? So we're going to use int though for later on because we want to be very specific about what we're doing. So to convert from, so here's the idea. We want to convert from years to minutes. And the way it does that, it goes, okay, in order to get from years to minutes, I need to take the number of years and multiply to the next best unit that I have, which is 365. We know there's 300, which is the number of days, right? We want to convert from years to days. We do that by multiplying by 365. And yes, we will address later that technically it is 365.25-ish days in a year, but that's much, much later for another lecture. But right now, years multiplied by 365 gives us the number of days in a year, right? So if we stop there, it would just print out that amount. Now then we got to convert days to minutes. So rather than going, I don't know how many minutes there are in a day, but I know how many hours are in a day. There's 24 hours in a day. Days times 24 gives me the total number of hours, right? Then finally, I know how many minutes there are in an hour, so I multiply by 60. And what we're doing is we're doing just this big equation over here, which is years times 365 times 24 times 60 step by step, just to make sure that I'm not messing up somewhere. All right. So the question is, how do I now switch this to print out the number of seconds? Go ahead and take like a minute on your own to kind of add on to this to add the number of seconds, right? What do we need to do there? We'll want to add another line, right? We went from years to days, days to hours, hours to minutes, and we can go from minutes to seconds. And we do it the exact same way, right? So go ahead and mess with that. Try going with putting a line right here to create the number to say, hey, this is how many seconds it is. So we add another line to our computation. And then the one other thing that if you're changing it to seconds, right, you'll want to change your print statement to reflect that. So take like 2 minutes to try that, and then I'll show you the answer there. Sorry about that. All right, so let's speed this up since we got only 40 minutes remaining. So now that we've got this, it's actually fair. Once you figure it out, it's fairly straightforward. We want to compute the number of seconds. So we can either add in right over here what we want to do, or we can start work from the back and go, we can work backwards, saying, hey, we want a certain number of seconds. Obviously, putting this in doesn't work. I say obviously, but it's obvious to me because I've been doing this for a while. But the reason, of course, this just doesn't work is that we haven't created a seconds variable. So we should do that and compute it. What is it? Well, I don't know how many seconds are in a year, but I know how many days are in a year. I know how many hours are in a day. I know how many minutes are in an hour. And I know how many seconds are in a minute. There are minutes times 60 seconds. And so if I go with 3 years, we'll see that that is about 94 million, which is about 60. If you do the math, if you can kind of mentally remember what we had earlier, that seems like the number we had times 60. So now, time for the trick. Change the problem as to why, and also as to why this is relevant for your homework. Change the problem to go the other direction. Given a number of seconds, how many years is that? So first thing we'll need to do is, and this one is where a lot of students get stuck, because that's tricky, because it's going to rely on math you haven't really had to do before. Enter seconds, receive num years, right? So we're going to need to just change this up, right? First off, we're going to, in fact, I'm going to go ahead and just delete all this right here. Given the number of seconds, we're going to give them the number of years. Let's also do this is equal to seconds, int, convert it, and print out seconds, that's our variable, comma, the word seconds is, and then years the word years. Now this of course doesn't work because, as I mentioned, we're going to have a variable that we are not defining. So let's define that. Well, I don't know how to, years, I want to go from seconds. Years is equal to seconds, then do some math, right? So we're going to leave that blank for a second, because I always like my programs to run, and especially getting the format and the framing of it correctly, right? Sometimes, even though that's silly to do, you write your introduction on an essay, then you write your conclusion, and then you fill in the middle, right? It's kind of like this. Years is equal to -1 seconds. Even though I know that's completely wrong, if I hit run now, at least it's running. 4 seconds is -1 years. We know this is a temporary variable or value. That's fine. Makes sense to everybody? I'm just putting -1 there because I got to put a number there. Actually, I could, I don't have to put a number there. I could put something like taco there. And now it's even more clear that that is just nonsense, right? I'm just putting something there to hold the value as we figure out what the math is. Okay. So let's go ahead and figure this out. Now, to go from seconds, to go from big units, from years to seconds, we did a lot of multiplication, right? We basically said, hey, how many big units? If we take a big unit, how can we split it apart into smaller units? Over here, we're going to be doing the opposite, which is given a small unit, how can I pack them into bigger units, right? For instance, we know that if I want to get the number of minutes that are in a second, sorry, the number of minutes that are in a number of seconds, I would take that number of seconds, and rather than multiplying, right, I would divide, right? And let's go ahead and just quick update, right? We can just simply, I want to see our progress as we're going. Minutes. All right, so if I put in 74, if I put in 632 seconds, it gives me that's 10.53 minutes. That's a bit problematic in terms of I don't know what a 5.3 minute is, but we will burn that bridge when we get to it. We'll fix that later on. We've got math going on. Let's go ahead and check out a value that we would know, like 90 seconds. That should be 1.5 minutes, right? Or we could do 180 seconds, which we know is around 3 minutes. We could do, let's see, one more. 246. We know that 240 is divisible by 60, so that would give us a nice solid value, and that 6 seconds would be a tenth of a minute. Okay, just using some basic math to kind of check on that. So to go from seconds to years, we are going to divide. So to get the number of seconds that are in minutes, sorry, get the number of seconds that are in an hour, we take the number of minutes we have and divide by 60. Then to go from days to days from hours, we would do hours divided by 24. And then to go for the number of years, right, we can finally get rid of the taco over here and say days divided by 365. So 6,000 seconds is a very small chunk of a year. What about, let's go with 90, that's 90, 000, 90,000, 000, 90 million. Okay. So there we go. We've converted from minutes, from seconds to years. But it's kind of an unhelpful format, right? What the heck is 0.85 years? Unfortunately, for this kind of computation, our months, our timekeeping system is not a decimal system. It's like a mishmash of different ratings. There have been attempts to make time a decimal system, and they've all failed horribly because we've all adapted to this by this point. So here's where the real part where students get messed up is Hans part 2, so that we can put it in a reasonable format. Print the number of years, months, days, and minutes. Not the number, not basically saying, hey, this is how many years it is, which is this many days, which is this many hours, which is this many minutes. No. I wanted to say, hey, this is this many years, and then put in it's this many days, right? I want to say it's this many years, days. I want to change this 0.85 into units of measurement that I understand. Now, part of the way we can do this, and we do have two tools to help us do this. They are integer division and modular arithmetic, the mod. If we convert this over to just doing integer division, watch what happens. Right? Let's go with 9. base 10. Oh, I hit a button while I hit the quotation mark while I was hitting enter. Is 0 years, 9 and 104 days. Because it didn't round up to year because I put in only 9 million. 0, 0, 0, 0, 0, 0, 0. Right? Second is 2 years, 1,041 days. We don't want to say that's how much. That's not necessarily what we want, right? We don't want it to say, hey, how many years is this? How many days is this? We want to say it's this many years, comma, days, comma, right? It should be a number less than 365 because if it's more than 365, it gets pulled into here. So this is wrong because it's a midway step. So how do we do this? Well, let's think smaller. Convert from seconds to minutes. Okay. Right? Seconds is equal to, right, not seconds, but minutes is equal to seconds divided by 60. Right? And let's go ahead and put in 120, 130 seconds. 130 seconds is 2 minutes, but really what we should be saying is 2 minutes, 10 seconds, right? There's a reason I'm being slow and pondering on this. Okay. So what I would like it to do now is print out instead of 2 minutes, 10 seconds. So how do I do that? And I'll let you work on that for like 2 minutes. Haha. But I'm gonna create a variable called remaining seconds, rem seconds for short. And what we do is that we essentially say we pack in as many seconds as we can into the minutes function. Sorry, into the minutes variable, which is 2. And then whatever's left over, we'll print that as our answer. So your question for the next minute or so is figuring out what goes right here. Now we used one tool, so maybe it's time for us to use the other tool. All right, so I'm going to wait for about a minute, and then I'll show you what I mean. All right. So remember, what we want is we've got our number of minutes here. And what we want to do is that we are taking that, we are dividing it by 60. We are taking our, we are taking our number of seconds here, and we are dividing it by 60. And that's going to give me however many minutes we have. But it's also going to leave us with a remainder of leftover seconds, right? So some value we'll call X, right? So we know that divide gives us this value. So the question is, what gives us that? What gives us that x, which is the modulus? Right. So what we do is we do seconds mod 60 to get the leftover amount. 135. 135 seconds is 2 minutes, 15 seconds. And so from here, we can kind of see a pattern on how to build up. Okay, let's go ahead and compute the number of hours it would be. Hours is equal to minutes. Normally, by the way, normally in these exercises, I give more time to students to do stuff. But with the way it works on Zoom, I've been finding that it's just been better to lecture normally um, and kind of do most of the work myself. So hours is equal to minutes divided by 60. We're going to pack as many minutes as we can into an hour. And whatever is left over, that'll become we'll keep that in a variable. Remaining minutes is equal to minutes. Oh yeah, it's going to be on YouTube. Don't worry. I'm recording it right now. Mod 60. And the code will be shared with you. Now we need to pack the hours into the number of days. Days is equal to the number of hours we have divided by 24. And remaining days, whatever's left over, not remaining days, but the remaining hours, what couldn't be packed up into a day, will go into here. Hours mod 24. Then finally, pack the number of days we can into a year. There's 365 days in a year. Remaining days is equal to the number of days that we could not pack up in there. Let's go with, and now we've got to change our print statement, which is seconds is equal to years, and let's go ahead and break this up into multiple print lines so that I can actually read it. It's annoying to do it like that, but print years. It will make sense. Print rem days, rem hours, rem minutes, print rem seconds. I know that's a lot of code, relatively speaking, but we're printing out a lot of information here. So 90 million seconds is 2 years, 311 days, 16 hours, and 0 minutes. Let's go ahead and do 90 million, 000. And now let's go with adding on another 10.5 minutes, which would be 630 seconds. So there we go. 2 years, 311 days, 16 hours, 10 minutes, 30 seconds. Now, what's cool about this, and why I spent so much time on this one specifically is the fact that, right, this is very similar to what you have to do for one of your homeworks, which says, given the number of seconds, compute the number of hours. And I think you should be able to do that. So now I'm going to hit the share code button. So yes, you might be wildly trying to copy this down or asking me to share it with you. It's already shared in here. You just have to refresh, or when you re-access the page, you'll be in your timeline shared at 2 minutes, 58 seconds or so. All right. So doing that last exercise, doing all this exercise has taken much longer than I expected it to, but hey, that's fine. So let's go ahead and talk about these kind of problems that we sometimes come across. And I'll go ahead and do this because we lost a bit of time waiting for people to join, and then me spending time on last lectures thing. So how many trees? So there's a lot of annoying interview questions you need to get, like why are Manhug covers round? Um, you know, how many houses are in the Empire, how many houses could you fit into the Empire State Building, or how much does the Empire State Building weigh? So questions like that. This is one of those, how many trees are in the state of Washington? Now this one's annoying because you can't really, get a good answer for that because you don't necessarily know, right? Can't really go out and do a census or a reasonable one and count all of them. But the idea here is that it's not asking about trivia. It's asking, how do you go about making that estimation? How do you go about making wild guesses that are somewhat accurate? And there's a comic artist called Randall Munroe, and he does a comic called XKCD, and we can see that he does these kind of questions all the time, and he writes books about these kind of things. What if and how to? If all the digital data was stored on punch cards, which are these old things, which is how we used to store computer programs, and that's even before my time. But if all those the digital data was stored on punch cards, how big would Google's data warehouse be? Now, this was written back in 2010. Um, and he basically says, well, I'm not sure. Here's the only other people who might be bigger than Google. The NSA, the NRO, which is yet another agency that we have, the National Reconnaissance Office. They stay out of the news quite a bit though because of their stuff. Let's see, Schlumberger, 10%, 10 cents, Chevron. And again, this was written quite a number of years ago, and he goes through his kind of ballpark math and research that he does, saying, okay, they've done this much, they've consumed this much in megawatts of power. How much does a server use? How much does space can a server hold? And he gets down to, okay, that means that basically Google has about 10 exabytes. So what does that? A box of cards sold 2,000 cards. A card has 80 characters. A character is a byte. And so basically does the math and says, right, so that'd be enough to cover New England to a depth of 4.5 kilometers, which is, points out that's big, bit deeper than the ice sheet during the last advance of the glaciers. Um, so it's a very interesting kind of question. So how do you go about like figuring out how many trees are in the state of Washington? Well, first off, if you're on the East Coast, we're in a bit of a jam because you're not necessarily familiar with the topography or geology or the biomes of the West Coast. It's a big country, a really big country. I'm booting up a incognito window so that when I pull up Google Maps, you aren't going to see my home address. So give me a second to reshare. So here we are. So the US is pretty big, and let's go satellite view for a second. Boom. We got green over here on this side of the country. We got brown and yellows and oranges here. And then again over here on the other coast, it's green again. Now let's click the state of Washington here. and get it all highlighted. So let's kind of work on this together. About how much of the state of Washington would you say is tree here? Right? About how much of this, like percentage wise? About half. Yeah, I'd go with about half. Just for, yeah, 50%. Make the math easy. It's actually a pretty good solid percentage over here. Like we could move this chunk over here and suddenly we have this. Also point out just some very interesting border incongruities here. It's very funny how these things end up. You got like a piece of the US over here, Port Roberts, which is all the way, which is physically attached to Canada, but not attached physically to the other parts of the US, which I'm sure makes commutes very interesting. Borders are weird. So anyway, we've got this. We've got about 50% of this being tree. Let's assume for the sake of argument that the amount of trees in this area, while existent, is fairly negligible, right? While trees exist in like, let's go ahead and go to, let's see, right? We've got urban buildup in Seattle, but and there's trees there, sure, but that's a negligible amount. So basically, we're just kind of saying, okay, all the trees are in the forest for simplicity's sake. And then if it's not forest, we're going to assume it doesn't have any tree. I know that's not fair, but again, we're just trying to make our assumptions for the sake of argument. So we've got, and now we say 50% of we'd say 50% of this is forest. So that gives us two questions we need to look at. What are those two questions? First is, how big is Washington? That's our first question. How big is Washington? Because we can figure out, okay, then that half is that. And then the other question, as Christopher just pointed out in chat, trees per acre. How many trees are in what is the density of trees in forest, right? So, two separate questions, but we can answer those fairly easily. The first one, fairly easily answered. Let's go to Wikipedia, very quick, nice and easy for those kind of things. Generally speaking, people don't go and vandalize generally speaking, when people vandalize Wikipedia, they aren't vandalizing the total area of the state, which we care about land area, so we'll go over here. I'll copy it in chat so I have it easier for reference, which is, it is this many kilometers. I'll go with kilometers, and if I have to change that value, then that's fine. Okay, so that is how many square kilometers are in the state of Washington. Okay, next, we need to go and look at how many trees per acre in forest. And that's honestly something we got to Google. We could kind of do estimation in our heads via, with our math and maybe say 100 trees per acre. But like, do you know that? Most of us are city folk, right? $80, $50 to 80 for 100 for a healthy mature forest. Hundreds or even thousands in younger and denser strands. So now that we've got that, so let's go ahead and say, so let's say 100 trees per acre. Okay. Let's go with, now we need to ask one more question, which is, because they've got different units, kilometers to acres. 1 square kilometer is 247 acre. Sorry, here we go. So let's go ahead and go back to the other window with the code. Right? So we've got ourselves our area. is, let's go ahead and do 172,587. That's the number of kilometers. Let's go ahead and convert that to acres. It's equal to area times, there's 247.1 acres per kilometer, square kilometer. Then we're going to do the math and say there is, oh, missed a step, right? We only want half that area, half that land mass, right? Got that many acres. Then we need to do let's see what we got. Print area. Definitely not. Oh, that's how many acres there are. And now we need trees per acre. Let's go with 100 for now. Which gives us quite a number of trees. 1, 2, 3. That gives us about 2 billion trees in the state of Washington, approximately, which is consistent with answers I've gotten in the previous semesters. All right. I'm going to go ahead and share this code. And I think I am done for the day. What I'll do is I'll make it so that this doesn't get checked off when we run the grader. Just be sure to fill out this final part. And then that's it. So I am going to go and run, and I will upload this recording later. Have a great day.